student. Today I am going to discuss about the when a current carrying loop placed inside a uniform magnetic field torque experienced by the loop. Okay. Here, see in figure 1, we have considered a current carrying loop, rectangular loop A, B, C, D. Here, length of the loop we have considered L, small l, breadth, small b, area, capital A, and current is flowing in anti-clockwise direction, and here it is placed inside a uniform magnetic field. Uniform magnetic field here produces by it is placed in between North Pole and South Pole. So here uniform magnetic field is denoted by vector B. Okay, so when it is placed, this is this is the rectangular loop, current carrying loop. Okay. Now, when there is no magnetic field, it is placed like this. But when it is placed inside a magnetic field, it experiences torque, and any instant of time, it displays from this position to that position like this. Okay, due to torque. And we have considered that any instant of time, this rectangular current carrying loop making angle theta with the direction of this magnetic field. It means the plane of the loop, angle between the plane of the loop and the direction of the magnetic field is theta. Here it is denoted by this, and this is theta. Okay, and this current carrying rectangular loop can rotate. This is the current carrying loop. Okay, this is length, this is breadth. Okay, now magnetic lines of force passing like this, and any instant of time it is making angle like this, means angle between the magnetic direction of the magnetic field lines and plane of the loop is theta. Now, okay, now it and this is xy is this vertical line passing through the center of this current carrying loop. So it is rotated like this vertically along the vertical xy axis. Okay, so it is shown here xy axis. Okay, now as it is placed inside a magnetic field and it is consists of AB, BC, CD and DA conductors, so every conductor experiences a force. Okay, now force on AB conductor, this conductor. Okay, direction, and this force is denoted by vector F1. How we have to first find the direction of this F1 force. Now, current is flowing along this direction A to B. Okay, like this. Now, direction of the magnetic field like this. Now, if we use the right hand thumb rule, then thumb gives the direction of the force, which is vector F1. Okay, this is F1, this is F3, F2 and F4. Okay, so F1, vector F1 equal to I within first bracket vector B cross vector capital B. Small b is the breadth and capital B is the direction magnetic field. Similarly, force on BC, force on this conductor BC. Here, direction of the current along this direction and direction of the magnetic field along this direction. Okay, so if we apply the right hand thumb rule like this, okay, so thumb gives the direction of the force experienced by this conductor BC. Okay, so here in this figure 1, it is F2 denoted by F2 and it is into the plane of the board, but in your copy it is into the plane of the paper of your copy. Okay, so F2, direction of F2 along this direction into the plane of the board. Okay, and this value is F2 equal to I within first bracket L vector L cross vector B. L is the length of this BC conductor, which is equal to length of this rectangular current carrying coil. Okay, now we have to find the force experienced by CD conductor whose length is B. Okay, the force on CD, it is denoted by vector F3. Okay, now again we have to apply the right hand thumb rule. The direction of the current along this direction C to D and direction of the magnetic field along this direction. So if we apply the right hand thumb rule, it gives the direction of the force F3. It is along vertically along this direction. Okay, now so it is written over here, and force on dA. dA means this d to a. Here direction of the current vertically downward and direction of the magnetic field along this direction. So if we apply the right hand thumb rule along like this, okay, the direction of the magnetic field along this direction. So thumb gives the direction of the force F4. Now what is the direction of F force? Like this, away from this plane of this board. Okay, it means along this direction F4. So this is the direction. These are the direction of the magnetic field acting on this current carrying conductor. Okay, now see, F1 and F3 are line of action of F1 for vector F1 and vector F3 along every point. Along here it is along this direction. If we go along this point along this direction, so line of action of F1 force and F3 force along the same line of action, and they are same but they are opposite to each other, so they will cancel to each other. Okay, so now but here F2 force and F4 force, what happened? Their line of action is not same and they are opposite to each other like this. So due to these two forces, this force act as a torque, equal and opposite direction, and their line of action is different. So due to this force, this rectangular current conductor will displace, or it will experience a torque like this. Okay, so from the definition of torque, we know that tau, it is denoted by tau, either force and perpendicular distance between their line of action. So tau equal to BIL, capital BIL into CE. Okay, and it is shown in figure 2. See, the DC, we have drawn only DC, the direction of F2 and into the from the C point into the plane of the board, and F4, it is acting from D point, it is away from this plane of this board. Now due to these two forces, equal and opposite force, and their line of action is different, so due to this force, this current carrying conductor experience a torque. Now tau equal to BIL into C BIL, B cos theta, right? Okay, C equal to this is right angle from geometry, and this angle is theta, so we can write B cos theta. So BIA cos theta, A is the A equal to area of this current carrying rectangular conductor, A equal to L small l B. Okay, so this is the torque experienced by this current carrying rectangular loop when it is placed inside a uniform magnetic field if the current is flowing in anti-clockwise direction. Now this torque expression of torque is tau equal to BIA cos theta. Okay, now if we are considering here single coil, if the number of turns is n, small n, then total torque is equal to tau equal to n times n BIA cos theta. Okay, so this is the torque experienced by this n a coil whose number of turns is n when it is placed inside a magnetic field, and if the coil is carrying current I in anti-clockwise direction. Okay, now we have to derive the vector form of this torque. To derive the vector form of this torque, because torque is a vector quantity, so we have drawn again this rectangular current carrying coil in figure 3. Okay, now theta is the angle between the direction of magnetic field and the plane of the current carrying loop. Okay, now here area of this coil is A. Okay, area is a vector quantity. Now here alpha is what? It is the angle between the direction of the magnetic field and the normal of this rectangular loop. here direction of normal of this rectangular loop, it is denoted by OM along this direction. And direction of the magnetic field, so angle between direction of the magnetic field, uniform magnetic field, and the normal of this coil is alpha. Now from this figure 3 we can see that theta plus alpha equal to 90 degree. So alpha we can write 90 degree minus theta. So taking sine alpha, sine on both sides, so sine alpha equal to sine 90 degree minus theta. So sine alpha equal to cos theta. Now we already derived this expression, tau equal to BIA cos theta. So tau equal to BIA, in place of cos theta we can write sine alpha. Okay, so tau equal to MB sine alpha. Here M is magnetic dipole moment. We know magnetic dipole moment equal to I and A. Okay, here A is the area and I is the current flowing through this loop. So in vector form we can write vector tau equal to vector M cross vector B. So this is the expression of torque experienced by point it is placed in a uniform magnetic field. Okay, so you just go through this and you have to visualize these things to derive this formula. Okay.